The exciting finding here is that, first of all, we're studying jumping spiders. It's been known for a long time that they are quintessentially visual creatures. A group of students self-assembled in my lab. These are the authors on the paper. And we got involved in their vision. And so, but what we did, which we weren't able to do when we studied them earlier, is that we decided that we were going to go after the neurobiology. We wanted to know what the nerve cells in their brain were doing. And in order to do that, we had to do something new. And that's what my then graduate student, Gil Menda, was able to do. What Gil was able to do that nobody else had been able to do is to make recordings without causing a blowout of the spider. Now, the term blowout is deliberately chosen because the body of the spider, like a tire pumped up, at least in my day, they were pumped up, it's under positive pressure. So what Gil did was to develop a method of making a very tiny hole first in the spider, through which he introduced an even tinier, a metal microelectrode to record from the brain. And so we were having great fun just understanding how the brain was processing visual signals, which we broadcast or we displayed on a video screen, and the neurons were ticking away. And this was great stuff because nobody had been able to do that before. Along the way, however, Gil and Paul Shamble, my graduate student, would be thumping their chairs around and saying, "Oh, look at that! Should we change the visual stimulus?" And amazingly enough, some of these neurons talked back. They chattered back when they heard these sounds, and that was really pretty remarkable because the received wisdom at that point was that spiders can't hear sounds. Paul was in the room too, said, "Wow, this is very impressive." So then Paul clapped his hands together, which is white noise. That contains frequencies. Of all amplitudes, and low as well as high. And sure enough, they responded to the clapping of the hands. So then we fine-tuned it, and then Gil and Paul used pure tones then to define just what these cells in the brain were tuned to, and they were tuned to quite reasonably narrowly to a range of sounds from about 80 hertz to about 130 hertz. What's special about those frequencies? When we looked at the data and said, "Gee, it's many low frequencies," we started talking to our colleagues, and one of our colleagues, a graduate student named Kevin Loop, said, "Oh, well, didn't you know that jumping spiders are the favorite prey of particular kinds of wasps?" And that immediately, so then we put two and two together. The wasps really prefer jumping spiders, and so we decided to check out the flight frequencies of wasps, both in the library and in nature. And it turns out that the particular wasps that seem to parasitize, that seem to prey upon jumping spiders, are at quite low frequencies, going down as low as 80, but going up as high as maybe 120, 130 hertz. So now we have a biological connection, a predator and a sound sensitivity, and that led to our behavioral experiments. However, the problem for us in having this embarrassing result, the spiders can hear, is nary an eardrum has ever been found. Their ears, what they do hear with and what they hear near field sound with, are hairs from their legs. They're called trichobothrial hairs. And so these are the hairs that we already know are sensitive to vibrations, and they're sensitive to direct touch. You don't see the hairs move, the trichobothrial hairs move, but if you immobilize them by, say, bringing down a small drop of water on top of it, so that now now the sound will bounce off of the water, which it does by about 90% or more. This essentially prevents the hair from moving, even though it's still attached to the spider and the nerves, and the neural response in the brain goes away. Now you wick up the water and the response comes back. And so this seems to indicate, was satisfactory to us to show that they could respond to vibrations in the air. By putting electrodes in the brain, and so using the brain as an assay for auditory sensitivity instead of behavior, we found that indeed spiders can hear sounds at a distance, something they weren't supposed to be able to do.